In this video, I want to show you how bifurcation theory can help in analyzing a real biological model. So we're going to look at a mathematical model of a fishery. So that's some area of the sea, say, or a lake, where fishermen are given quota to catch seasonal fish. And the government has to decide how large a quota to give for the annual catch. And we'll see that because the equation is nonlinear, it exhibits certain bifurcations which have a big significance as to how much of a quota the government should be giving. So let's try to write down a model here. So let's n of t then be the number of fish, right, at time t. And we want to write down a model for n of t. So we're going to start with the logistic model, which says that when fish are rear, they grow exponentially. And then when they get to a certain value, they approach a constant population that's equal to the carrying capacity of the population. So K is the carrying capacity. So when n is small, we get exponential growth, and then eventually n approaches K. So if you look at a graph of the logistic model, let me draw that up here in red. The logistic model will have this characteristic S-shaped graph. So this will be our carrying capacity K. Okay? So exponential growth to a carrying capacity K. So that's what happens in the absence of fishing. Then if we include fishing, we can assume that a constant amount of fish is caught per unit time, or say number of fish caught per year, when the fish population is large. So when the fish population is large, we have a constant amount of fish caught per year. So dn dt would have a minus c term here. And that would be fine as long as n is large, say at the carrying capacity of the environment. When n is around k, you would get c fish caught per year, probably due to the fishing quota set by the government, c fish per year. But if n is small, right, so if you overfish and you drive the fish population down to a small value, the fishermen won't be able to catch their quota. So we would like this extra fishing term to go to 0 with n. So we can modify this term by making it go to 0 with n, while at the same time going to c when n is large. So we can also put an n in the denominator here and add to it some constant a, which is small, but it serves the purpose of when n is around k, n would be much larger than a, and we would catch c fish annually. Fishermen would catch c fish annually. But when n is small, a would be large relative to n, and this term would go to 0 linearly with n. Okay? So this is a reasonable model then for a fishery. We can non-dimensionalize the model in order to reduce the number of free parameters. So R has units of 1 over t, n has units of fish, number of fish. So we can define, say, a non-dimensional time, tau, by r times t, and we can define a non-dimensional fish number, x, by n over k. And if we non-dimensionalize the equation using these variables and do the substitution, what we'll find is an equation for x. So we will end up with dx d tau equals x times 1 minus x, which is the non-dimensional logistic equation. And then this term here will be a non-dimensional c times x over a non-dimensional a, which is alpha plus x. So here, if I do this in red, this little c is going to be non-dimensionalized big C. C has units of n over t, so it will be big C over rk. And the non-dimensional a is going to be alpha, which is a. A has units of n, so it's a over k. Okay? And then we end up with a non-dimensional equation. So let's start with this then. This is our non-dimensional equation. So we want to analyze this, and we want to analyze this by finding, we want to find the stable fixed points, or the stable equilibria of the system, right? And that will be the values of x, where dx d tau is equal to 0, and where those x star, those are stable to small perturbations. And that will basically tell us what is the fish population at equilibrium. So to do that, we start by looking at fixed points of this equation. So dx d tau equals 0, so this equals 0. So we have x times 1 minus x minus cx over alpha plus x equal to 0. Each term is proportional to x, so we can factor out x. We can multiply by alpha plus x, so x times 1 minus x times alpha plus x minus cx equals 0. Sorry, this x I already have. So I factor out, let's factor out that x. So we have here, so I factored out the x. Okay, so we want the fixed points of this, and we get, then one of them is x star equal to 0. That's a fixed point. That means no fish. So this is the case of the fish going extinct. And then we have this internal quantity equal to 0. This is a quadratic. So if we multiply by minus 1, that will be x squared. And then x minus alpha, 1 minus alpha. So that will be plus, and then multiply by minus 1. So alpha minus 1 times x. And then minus alpha plus c, so plus c minus alpha equal to 0, right? So we had a minus x squared became a plus x squared, a minus 1 minus alpha plus 1, or 1 minus alpha becomes an alpha minus 1, and then a plus alpha becomes a minus alpha plus c. Okay, so this is our quadratic equation. So then we have two roots, so x, the fixed points, and there'll be two of them, a plus and a minus. Negative b, 1 minus alpha, plus or minus the square root of b squared, 1 minus alpha squared, this is a 1 minus b squared minus 4ac minus 4c minus alpha over 2a over 2. Okay? So we have 3 fixed points. All right, 3 fixed points. And when are they valid? So x star equals 0. This is, we're looking at for variation of these fixed points as a function of c, the amount of fishing that's being done. So this is valid for all c, right? And then the second fixed point is valid only if this one is a square root of a positive number. So this thing here is valid only when this is greater than 0. So 1 minus alpha squared minus 4c minus alpha is greater than or equal to 0. When is this valid for c? So that means that we pull a minus 4c over to the left, over to the right. So 4c is less than or equal to 1 minus alpha squared plus 4 alpha. This is 1 minus 2 alpha plus 4 alpha plus 2 alpha plus alpha squared, which is 1 plus alpha squared. So that means that c has to be less than or equal to 1/4 1 plus alpha squared. Okay? So you only get this these two solutions provided that c is smaller than 1/4 1 plus alpha squared. And then when the x has to be greater than 0, right? The equilibrium has to be greater than 0. When is this greater than 0? Well, the plus root is always greater than 0, right? But the alpha is smaller than 1, so the plus root's always greater than 0. The minus root is only greater than 0 if this thing is, this c minus alpha is positive. So 1 minus alpha minus 1 minus alpha squared minus something. This has to be positive. So c will have to be greater than alpha. Okay? So this one, so minus root valid only for c greater than or equal to alpha. Sorry. C greater than or equal to alpha. So let's put it together then. So we have x star equals 0. So we have the region c smaller than alpha. We have the region c between alpha and 1/4 1 plus alpha squared. And we have the region greater than that. So we have c less than alpha. We have 3 roots, right? We have x star equals 0, and we have x star equal, we have only 2 roots because we don't have the minus root, we have the plus root. So we have x star plus. So let me just write that as x star plus. Okay? When c is smaller than alpha. And then when C is between alpha and 1 plus alpha squared over 4, or 1/4 1 plus alpha squared. Then we have three roots. X star equals 0, X star equals X star plus, and X star equals X star minus. And finally, for C, greater than or equal to 1/4 1 plus alpha squared, the square root became negative of a square root, so we just have X star equals 0. So we have 2 roots here, 3 roots here, and only 1 root here. Okay? So let's try to draw a bifurcation diagram. So let me draw a bifurcation diagram. So let's come up here and clear the screen. So a bifurcation diagram can look like this. So our bifurcation parameter is C, and we're looking at the fixed points. At some value, well, we have C equals 0, X star equals 0 is always a fixed point. We have at some value, when the square root becomes real, we have a bifurcation happening that looks like this. Okay. This is a saddle node bifurcation. One of the branches is stable, one of the branches is unstable. If you extend this back to C equals 0, this will come back and hit the axis at exactly 1, which means that no fishing, the population will grow up to the carrying capacity. And that's what we expect. So we expect this upper branch to be stable, this lower branch to be unstable then, and hits x equals 0 at exactly the value of alpha. Okay? This value where the saddle node bifurcation occurs is 1/4 1 plus alpha squared. And these are 2 of the fixed points. And then the last fixed point is x star equal to 0. This one we expect to be stable when the fishing is very high. So it's stable out here. And then another bifurcation must occur at alpha that is called a transcritical bifurcation. And at this point, x star equals 0 must become unstable. So we've got 2 bifurcations here. We've got this one, which is called a saddle node bifurcation. And we have this one, which is called a transcritical bifurcation. Okay? So what does this mean for our fishing model? So let's say that there aren't that many fishermen, so not that many fish get caught. So C is small, so maybe we're somewhere over here. So we have a very robust fishing population, okay? So now fishermen are making a lot of money, so other fishermen want to fish. So more fish get caught, and the government institutes some quota. So where should the government put their quota? How much fish should be allowed to be caught? Well, you want to have some sort of balance, right? You want a large fish population so everybody can catch fish, but you want the fishermen to be successful, to catch a lot of fish. So you like to have the quota large, but not so large that we crash the fish population. Because the problem here is that then if you increase the quota beyond a certain point, let's say to here, then what will happen is that the fish population can crash. So this is a jump bifurcation. Right? If you make the fish quota too large, you will no longer have a stable equilibrium of large numbers of fish, and you can, in the subsequent year, after you've increased the fish quota, you can crash the fish population in this jump down to x star equals 0. So to learn something from this model, you would say this is a nonlinear model, can have very nonlinear effects. If you increase the quota just a little bit, it's possible that you can end up crashing the fish population in subsequent years. So the government must have some caution.